Hello there. In this video we're going to discuss how to calculate the circumference of a circle, or how to really derive where this 2 pi r equation that we've grown up to know actually comes from. And this proof is just going to be based on integration and the arc length formula for curves. Alright, so we're going to approach this proof just like we did for the area of a circle proof. So we're going to consider a curve or a circle in the plane. And we're going to consider the top half of a circle so that this is a function of x. So this function of x is going to be equal to the square root of r squared minus x squared, where the radius of this circle is r. So we want to find the arc length of f on this interval. So the arc length, pretty much the circumference of the circle, is going to be 2 times this arc length of f on minus r to r. So that's the first observation that we have. And remember how to find the arc length of a curve. So that's going to be equal to 2 times the integral from minus r to r of the square root of 1 plus dy dx, the quantity squared, with respect to x, where dy dx is the derivative of that function that we specified earlier. Alright, so let's find the derivative of that first. So if y is equal to the square root of r squared minus x squared, so what is the derivative of that? So the derivative of the square root by the power rule is going to be 1 divided by 2 times the square root of r squared minus x squared. And then we're going to multiply by the derivative of the inside by the chain rule, and that's going to give us minus 2x. So if that is true, then that means dy dx is going to be equal to minus 2x divided by 2 times the square root of r squared minus x squared. We can cancel out these 2's to make things a little bit more easier for us, and that's just going to give us minus x divided by the square root of r squared minus x squared. Since we need to square this in the arc length formula, we might as well square it here just to make things simple. So dy dx squared is going to be equal to square the top, becomes x squared, square the square root disappears. And that gives us that. Alright, so now we're going to go back to our integration formula to sort of finish out the proof. So c is going to be equal to 2 times the integral from minus r to r of the square root of 1 plus this term. So x squared over r squared minus x squared with respect to x. For this radicand, we're going to get a common denominator. So we're going to have this as 1 over 1. And we're going to multiply top and bottom by r squared minus x squared. So once we have that, we're going to have the integral from minus r to r of the square root. So we're going to have r squared minus x squared over r squared minus x squared plus x squared over r squared minus x squared with respect to x. And as you see here, once we combine like terms, this minus x squared and x squared are going to cancel each other out directly. And we're just going to be left with c is equal to 2 times the integral from minus r to r of the square root of r squared divided by r squared minus x squared dx. Now once we take the square root of r, so the square root of r squared is going to just be r. R cannot be negative, so we're just going to take the principal square root of that. And then we're going to factor that out of the square root. So we're going to have c is equal to 2r times the integral from minus r to r of 1 divided by the square root of r squared minus x squared dx. And now comes the trig substitution that is similar to the area of a circle proof. So we're going to let x be equal to r sine theta, which is going to force dx to be equal to r cosine theta d theta. And once we have our limits of when x is equal to minus r to r, we can find that theta is going to go to minus pi over 2 to pi over 2. Just, solving those equations for theta once you solve, plug in x. And also a third, so 1, 2, and 3. The square root of r squared minus x squared is going to be equal to r cosine theta. And you can work through the process to actually see that that is true. But if you're, iffy on the details, check out the area proof, and we proved it there. All right, so that means what? So c is going to be equal to 2r times this integral from minus r to r of 1 divided by r cosine theta times dx, which is r cosine theta d theta. Oh, these limits should be different. So this should be minus pi over 2 to pi over 2, since we're in d theta now. All right, so what do we have here? So this r cosine theta term will cancel, and we're just going to be left with c is equal to 2r times the integral from minus pi over 2 to pi over 2 of 1 d theta. So the integral of 1 with respect to theta is just going to be theta, so we have 2r times theta, and that's going to be evaluated from minus pi over 2 to pi over 2. So, evaluating our limits, so we have upper limit pi over 2 minus negative pi over 2, and pi over 2 minus negative pi over 2 is just going to be equal to pi, half and half as a whole. So that means what? So that means the circumference of the circle is going to be equal to 2 pi r, which is the result that we were aiming to prove. And of course, this gives you the length of any circle, no matter where it is located in the plane. It'll give you the length of that perimeter for that circle. And that's how to prove it using trig substitution, the arc length formula, and integration.